Okay, welcome back to this week's online lecture. This is the 5th week, so I hope by now you got familiar with this flipped class learning style. Okay, the title of this week's lecture is chapter 26. It is current and resistance. And then let's first review what we have studied the last lecture. The most important topic last week was a capacitor. So we learned what a capacitor is and what it is for. Remember that capacitor is a device which stores electric charges. And then we also learned the definition of capacitance. What was the definition of a capacitance? Capacitance was the amount of charge stored divided by the potential difference. Okay. And we also learned how to calculate capacitance of a capacitors with simple shapes, parallel plate capacitor and cylindrical capacitors. These are the simple shapes we have studied. And also how to calculate capacitance for many capacitors connected to each other. Okay. And we also studied how much energy stored in a charged capacitor. And finally, we learned what happens when a capacitor is filled with a dielectrics. So remember what happened? The capacitance could increase by filling the capacitor with a dielectrics. Okay. And in this lecture, we will discuss what electric current is and study the Ohm's law, which defines the resistivity. And we will see what happens when current flows in a resistive circuit. And we will finally learn there are various types of conducting materials. Okay, let's try another simulated experiment. This time, this simulated experiment is about the circuit with battery and a resistor. Okay. Here in this simulation, we have a battery and some kind of material which are connected by wires. Okay, and this battery can supply electric potential of 2.88 volts. Let's play. Okay. Now, some things are moving, right? So these small dots are coming out from the negative terminal of the battery, and this goes through and then comes back into the positive terminal. What do you think they are? Right? They are electrons. We say the current will be flowing from the positive terminal into the negative terminal. But in fact, electrons are negatively charged. And most of the time, what is flowing in the current are electrons. So remember that the direction of the electrons flow is in fact opposite with respect to the direction of the current flow. Okay, that's something you have to remember. And here there are some green and larger spheres which are bouncing off, right? What do you think they are? They, in fact, represent atoms in this material, which are actually bouncing off. And then at the same time, they are colliding with electrons, so they make the electron flow difficult. Okay, this is the actually this phenomena is more or less like resisting the current flow. So that's why we call it resistance. And then this material is a resistor. Okay. And then here, let's see what we can do. Let's try to actually change the voltage. If you change the voltage, and then let's make it say up to 9.12, and then you can see that the electron flows is moving faster. Okay, I forgot to mention that this meter measures the amount of current, which is the amount of charge flowing per unit time. And as you can see, the number has slightly went up. And then you see that the bouncing off of these atoms became larger. And then the color has actually changed. This color represents that the temperature has changed. We will see later why the temperature is changing here. What has temperature got to do with this electricity? Okay, we will see that. Okay, and then I can put it back down, and then let's go back to the original value where we were. We were at 2.88 volts. Okay, and then now you see that the temperature has gotten colder back. Okay, and then let's try another thing. actually here we can change the resistance of this material, which means that by increasing the resistance, we can make this electron flow more difficult. Let's see what happens if you increase the resistance. Okay, I made the resistance twice. As you can see, there are some twice more of these green things. Okay, and then they are blocking or actually resisting the electron flow. So from the viewpoint of electrons, it is more difficult to flow. Okay, and then of course if you reduce this resistance down to 0.2, you see there are not many. There are just 3 in this figure. So electrons feel it is a lot easier for them to flow. Okay, and then at this situation, the current flow will become larger. Okay. So we have just seen the simulated experiment about the conducting electrons, but in fact what we have just seen is more like a cartoon with a lot of approximations. Okay, so we will discuss now in detail what actually is going on when the electrons are flowing. Okay, the first thing, how fast are the free electrons will be moving? Well, in the simulated experiment, it looked like the electrons were moving not very fast, right? But in fact, free electrons in conductors, actually, they can move very fast. The speed at which they are moving is approximately 1,000 kilometers per second. It's very fast, right? But in fact, the reason why the simulation showed as if the electrons are not moving very fast is the following. Okay, suppose there is no potential difference in the beginning. Even without potential difference, electrons are still moving, and then they are moving because of the thermal energy. At certain temperature, because of the kinetic energy associated with the thermal energy, the electrons will be moving at very fast speed. But then there is actually no direction, so they can move to any direction, so they perform so-called a random walk. So visually, it's more like this. Okay, they are moving at any direction, and after a certain period of time, it will have moved from the original position to the final position, and then we can show the net displacement factor like this, and then each black arrow represents the movement at very fast speed, but then eventually it's not moving very much, it's moving only by this much. And then remember, there are a lot of electrons, not just one, but Avogadro's number of electrons in this conductor. So, and then each of them, of course, will have no special direction. So if you combine all of them, it will just look like they are moving at any random direction uniformly, effectively. So therefore, there will be no net motion, so zero motion, right? And then suppose now we apply the electric potential, and then according to this picture, actually this random walk is so fast, so it's not changing much, but apply the electric potential only slightly modifies the motion. So therefore, if you take this circle as the original motion represented here, after applying electric potential, there will be electric field, and as a result, this net displacement will be something only slightly shifted to the positive direction, actually a positive side of the electric potential, which means it's shifted along the negative direction of the electric field. Why? Why negative direction? Because electrons are negatively charged. Okay, so this is the reason why we showed that electrons may be moving very slowly. And then, in fact, when you say current, actually this random walk, very fast random walk, does not contribute. It is only the net displacement, and especially the slightly shifted part coming from this electric field only contributes to the electrical current. Okay, this is what is actually happening. And then one more thing to note is that this is something we already said. The electrons are given negative signs due to the historical reasons. I think it was Benjamin Franklin who just happened to assign negative signs to electrons. and then as a result, a flow of electrons is equivalent to the flow of positive charges of equal amount along the opposite direction. Okay, so especially in this case, electrons will be moving in this direction, and then this is equivalent to the amount of positive charges flowing this direction. Okay, so and then these both of these arrows represent electrical current going this direction. Okay.